Hi friends, today let's see the statement and proof of Rouche's theorem. Rouche theorem is one of the very important theorem in complex analysis. So first of all, let's look into the statement straight away. So the statement is simply if f of z and g of z, if f of z and g of z are analytic function. So where is this analytic function? This analytic function within, we can say like within and on a closed curve C. We can say it is contour as well, contour of curve C, and along with that it should satisfy a condition, and mod of gz, that is length of the function gz, one of the function gz, should be less than mod of f of z, that is length of f of z, and this is specifically on C. So this should be on the path C. Then, so if this condition is satisfying, then what will happen is, so if this condition is satisfying, then the number of zeros, or else we can also say f of z and the function g of z plus f of z, so these are two functions, both these functions will have same number of zeros, inside or within, we can say inside or within C. So that's the simple statement of Rouche's theorem. So Rouche's theorem, let me repeat again. Rouche's theorem simply says if f of z and g of z are analytic function within and on closed curve C or closed contour C, and if it is satisfying this particular condition, that is mod of gz is less than mod of f of z on C, so this should be satisfying on C. So let me draw a figure of this so that it is much more clear to you. So let me draw a closed contour or a closed curve like this. So this is my contour C, right? So the condition which I am mentioning over here, this should be satisfied on this contour. On this contour means on this particular path. So on this path, if I take this function g of z, let's suppose say this is my g of z, and let me take some other function, that is f of z. So the length of g of z should be less than length of f of z on the curve C, and along with the means if this condition is satisfying, then what will happen? Then f of z and g of z plus f of z, that is these two functions will have the same number of zeros inside C. So let me clarify it again. What does this particular statement which means that if I pick up some zeros within this C, so zeros are particularly the points at which the function will give me answer 0. The function will give me value 0, right? So if I pick up some values from this curve, from inside this curve, so that's specifically inside. So if I pick up some value inside this curve for which my function f of z is giving me 0, so these values are called as zeros of this function. Similarly, if I pick up some values from this particular closed curve for g of z plus f of z, so for this function if I pick up some value such that when I put these values in this particular function, it should give me answer 0, so those values are called as zeros of this particular function. Then what will happen is the number of zeros which I collected over here for this function f of z and the number of zeros which I collected here for this function g of z plus f of z, both will be same in number. So if I pick up like 10 zeros for this function, I will have exactly 10 zeros for this function as well. So that's what Rouche theorem states, and that's what we are going to prove it in today's video. So let's straight away jump into the proof. It's very simple. So just some prerequisite or something extra additional that we need to prove over here, just to state that. So before moving into the proof, what I need to prove firstly is that so we will be counting all the zeros inside this curve, right? So this indirectly means that these functions will have no zeros on the curve. So that's what we need to prove first. We firstly need to prove that these functions will not have any zeros on the curve and then we will prove that these functions have some zeros inside the curve and both the functions are having same number of zeros. Fine. So let's first prove that these two functions f of z and g of z plus f of z, these two functions do not have any zeros on the curve. So let's prove that first and then we will move to the main proof saying that both of them have same number of zeros inside the curve. So let's start with the proof. So first of all, to prove anything, right, we just need to pick up a few of the given things from the theorem statement itself and then we will proceed ahead with the proof. So let's say suppose we have what, two functions, right? So suppose like f of z and g of z be two analytic functions. So we are just copying the same statement, analytic functions over or we can say analytic functions, yeah, over and instead of over we can use the same statement, right? We can say within and on closed curve C, within an on closed curve C. So along with that we have this condition which we need to satisfy. So let's say and mod of g of z should be strictly less than mod of f of z. So this should be on C. So let's write it down and then let's proceed further. So first we will prove that. So we can say firstly we prove, what should we prove? We prove that function f of z and g of z plus f of z do not have what they do not have any zeros on curve C. So let's prove that first. So we will use the method of contradiction to prove this. So we will say that we just need to prove that these two functions do not have any zeros on the curve C. So to prove that, let's say suppose f of z has a zero on curve C, and let's say it is z equals to a, right? Let's say it is z equals to a. So z equals to a is one of the zero. So this means that if I put this value of a inside this function, I will get my answer as 0, right? So let's say therefore f of a is equals to 0. So now since we have to prove that there is no 0 on this curve for this particular function, we should arrive to some contradiction. So let's see how we will arrive to some contradiction. So since we have this a on this curve, it will obviously satisfy this condition, right? So this is a condition which is satisfied on the curve C. So that means that this condition will be satisfied. So let's say therefore modulus the mod value of g of a will be strictly less than mod value of f of a, right? And we have just seen that a mod of f of a is nothing else but 0. So I can say this value is equals to 0. So what does this simply imply? So this will imply that mod of g of a itself is less than 0, right? So this is less than function mod of a, and mod of f of a is equal to 0. So indirectly it means that our g of a is less than 0. So g of a is less than 0, not only the g of a, mod of g of a is less than 0. So if you just think it logically, mod of any value can be either 0 or greater than 0, right? Mod of any value cannot be less than 0 at any instance. So we can say which is an absurd. So this cannot be accepted, because mod of anything cannot be less than 0. It should be either 0 or more than 0. So we can say which is an absurd. Absurd means it's something wrong. Absurd. So we can say therefore our assumption is wrong. So what was our assumption over here? So we were assuming that suppose that this function has a 0 on the curve. So we can say therefore f of z do not have any zero on C. So this should be specified, any 0 on C. So similarly, let's try to prove that the other function which is there, right, g of z plus f of z, we just need to prove that this function also do not have any 0 on this curve C. So let's try to prove that. So on the similar lines we can say, let's assume g of z plus f of z also, we can say g of z plus f of z has zeros, has a 0, let's particularly say has a 0 on C, and let's say it is the same, let's say this is z equal to a or z equal to b, anything you can take. We are just assuming that it has a 0, this function also has a 0 on C, and again we should arrive to some contradiction. Let's see how. So that means g of a plus f of a will give me answer 0. So that means therefore g of a, let me send this f of a over there, this will become minus f of a. Now we can say, right, because this a is nothing else but something on this a is nothing else but a point on this curve, so it should satisfy my hypothesis. So what's my hypothesis? It's saying that on this closed curve, on this C, my g of mod of g of z is always less than mod of f of z. So taking that into consideration, let us see what happens over here. So if I take mod on both the sides, what will happen? So as you all know, as we take mod, the negative will be removed off and we will have just these two values equal. But what is happening over here? This is basically contradicting our fact, which is stating clearly these values should be less, like this should be less than this. So that particular hypothesis is getting arriving to a contradiction over here. So we can say which contradicts our hypothesis. So we can say which contradicts our hypothesis, or we can say it contradicts our fact that this should be strictly less than mod of the value g of z should be strictly less than mod of f of z. So we can say therefore our assumption is wrong. So what the assumption is wrong? So what did we assume over here? We suppose that this function has a 0 on C. So this means that g of z and f of z has no zeros, right? Has no zero on, we can say, C, right? So that's what we have proved, like this function do not have any 0 on C, and also we have proved that the function f of z do not have any 0 on C. So that was the basic prerequisite that we need to prove in order to start with this particular theorem. So let's move on to the main part of this theorem. So we have just proved that these two functions do not have any 0 on this curve C. So now the main theorem comes in. So we just need to count some zeros for f of z, and we need to count some zeros for this function g of z plus f of z. And what should we arrive? We should be arriving to the final answer, like the number of zeros that we counted for this f of z and the number of zeros that we counted for this particular function g of z plus f of z, both are equal in number. So let's straight away proceed to that proof. So we can say like we need to prove the numbers are same, right? So we can simply say let we can say that n1 and n2, let n1 and n2 be the zeros of f of z and g of z plus f of z, right? So we can say respectively. So that means that this n1 is a 0 for is the number of zeros. Let's say let n1 and n2 be the number of zeros, to be specific, number of zeros for this function and for this function. So basically what we need to prove over here, to prove that we just need to prove that the number of zeros n1 for this function and the number of zeros n2 for this function are equal in number. So we just need to prove that n1 is equals to n2, right? So now let's try to prove this particular thing. We just need to have the number of zeros for this function, that is n1. We have to get number of zeros for this function, and then we just need to arrive that both the numbers are equal. So it's pretty much simple, but before that we need to know something. We need to recall some facts that we need to use while proceeding further. So let me write it over here. We need to recall something. So what do we need to recall? So let me f, g are the functions which I have already used. Just for recalling purpose, let me say some function, let me name it as p of x, something like that. So just to recall, if p of x is a analytic function within and on curve C, then you need to remember there is a fact behind this. So if p of x is an analytic function within and on curve C, then 1 upon 2 pi I integration of this function p of x with the numerator as derivative of this function p dash x d of x, d of z, or else we can take d of x as well, since the function polynomials are in x, or the functions are in x, we can take d of x. This will be equals to n minus p. So just to specify over here, n is the number of zeros and p is the number of poles, poles, number of poles, right? Poles are basically the points at which the function becomes absurd, or the function becomes meaningless, or we can say particularly the value at which the function's denominator becomes 0. So this is one thing which we need to recall, and along with that we need to recall one more thing, which is if a function is analytic within a curve, it can be any curve, within a closed curve to be specific, within a closed curve, then we can say that the function will have no poles inside this curve. Then the function will have no poles inside the curve, right? So I will come back to these two points again while proceeding ahead with the proof. So just keep behind your head somewhere, like these two are the things which we need to recall while moving further. So I will just have a quick overview for these two recalling section again. So what we need to recall is, if a function is analytic within and on the curve C, then this particular value will be equal to that is 1 upon 2 pi I integration of the function p of x in the numerator, the derivative of the same function p dash x dx will give me the value n minus p, where n is number of zeros, and p is number of poles, right? So just we'll keep this in mind, and along with that the other point which we need to keep in mind is, if the function is analytic within a closed curve, then the function will have no poles inside the curve. Fine. So let's proceed further. This will be the first thing which we will be using again now. So let's go step by step. We have two functions, right? What are the functions? We have f of z. So first let's concentrate on f of z. So let's use this particular formula in order to get the number of zeros for f of z, because we are concerned about n1, right? And then we will consider this particular function, and using this particular formula we will get the number of zeros for this function as well. So this is the formula which will give me the number of zeros which we are looking out for. So we can say, so we know, right, f of z is an analytic function. So this condition is getting satisfied. It's an analytic function within and on the curve C. All the condition is satisfying for this particular function. So I can simply use this formula and get my n1. So I can say, since f of z is analytic within and on curve C, within and on curve C, therefore we can also say like this, f of z has no poles inside C, right? So that means in this formula, this p, right, see, this p will be 0 for this instance. My p will be 0 basically. So we'll have no poles inside C. So let's try to use this formula. For my function f of z. So let me try to write it down. So it will be basically simple as 1 upon 2 pi I integration of the function over here f of z. To be specific, my function is f of z, and in the numerator I will have f dash z and dz, right? So this will be equals to n is the number of zeros. Let me try to recall for my f of z, what is the number of zeros that I am assuming? That is n1, right? So let me write it as n1 minus p. So minus p, number of poles I have just now specified over here. I will have no poles because it is analytic within this curve. So n1 minus 0, so that will be n1 only. I will just leave it over here. And let's proceed further for my second function. So my next function is this one, right? G of z plus f of z. So it's again the same. It's again g of z is analytic, f of z is analytic. So the addition will also be analytic. So I can again use the same condition for the second function as well. So I will say since g of z plus f of z is analytic, g of z plus f of z is analytic, you can say within and on the curve C. Therefore we can just write it like within and on the curve C. Let me write it down straight away. Within and on curve C, on curve C. So what will happen by doing this, like within and on curve C, my function is analytic. So I can simply say that therefore my function g of z plus f of z will have no zero, will have no poles, not zeros, will have no poles, in C. That means in this scenario also my p will be equals to 0. So let's try to write this formula again for this function. So it will be 1 upon 2 pi I. So I'm just trying to reiterate the same formula again for my second function. So as you can see below, denominator will be function and numerator will be derivative of the function. So over here I will write like this, like denominator will be my function g of z plus f of z, and numerator will be a derivative of the function g dash z plus f dash z dz. So this will give me the number of zeros minus number of poles, right? So in this case, for this function, what is the number of zeros that I am assuming? Number of zeros for this function I am assuming it as n2. So what I will do is over here I will say n2 minus number of poles. So as I said, since it is analytic function, the number of poles will be 0. So I am just not writing that minus 0, it will remain the n2, right? So so now we have n1, some value for n1 with me, some value for n2 with me, and what is my ultimate aim over here? My ultimate aim is to prove that n1 and n2 both are same. So as a part of Rouche's theorem, we just need to prove that both these values which we have right now with us, that is n1 and n2, both are same. So let's try to prove it right away. N1 and n2 both are same, right? So yeah, so we cannot directly jump into the proof, because we can easily see that this part is entirely different from this part, this entire part is entirely different from this entire part. So there are something which we require in order to prove them same. So instead of directly jumping into the proof stating that both of them are same, what we can do, we will just say that let g of z upon h of z. So this is the way how you need to proceed further in order to prove them same. So I can say let g of z, sorry, not h of z, right, f of z. These are the two functions which I have right now with me. Let g of z upon f of z be equal to, so since these are functions, their division will also be a function in z. So let me say these are equal to h of z. Fine. So what does this imply? So this implies simply g of z is equals to, when we multiply this over here, we will get f of z into h of z. So let me keep this handy with me. I will need this going further. And then the next thing which I need to specify over here, right, I just need to show that this h of z is, I can say, right, I can literally say that this h of z is analytic. Why this is analytic? Because we know this function is analytic, this function is analytic, because that is our theorem statement itself. So let me just show you guys, like the theorem statement itself says both of the functions which we are picking up are analytic functions. So over here also we can say, since these are analytic functions, their division should be analytic. So I can say therefore h of z is analytic, right? So let me say why this is analytic. So I can just give the reason over here, right? I can say since g of z and f of z are analytic. So this is the reason why the function h of z is analytic. Now there comes a question in your mind why we are doing this and what's the need of this h of z. So we will come to this h of z in a minute. So in this upcoming section of the proof, we will need this h of z. So let's proceed further. Yeah, so proceeding further, so as we all know, we just need to prove that n1 is equal to n2. So the simple way to prove that is we can simply say, right, if n1 minus n2 is coming to 0 or n2 minus n1 is coming to 0, then obviously they are same. So that will be the exact approach which we will be trying to get over here. We will try to land to a particular equation saying that n2 minus n1 is 0. So let's start doing that. Let's try to get n2 minus n1. Let's see what is n2 minus n1. So just to show it over here, n2 minus n1, right? N2 was this big thing over here. So let me write it down straight away. 1 upon 2 pi I integration of this thing. So let me copy it down over here. 1 upon 2 pi I. So this is my n2. 1 upon 2 pi I. Integration of g dash z plus f dash z upon g of z plus f of z. And guys, just remember, like whenever you are writing integration, go on writing the curve as well everywhere, because we are doing this integration with respect to the curve, so over the curve. So just try to be more specific while writing this integration sign. Put that curve sign over here. So we are just to notify that we are doing this with respect to this curve. Minus, what is my n1? And our n1 is, let's try to copy this entire thing over here. 1 upon 2 pi I integration of f dash z upon f of z dz. So this is my n1, right? So we have just copied the value of n1 and n2 over here. Now let's try to proceed further. So do we have anything over here? Right, we have the value of g of z, right? We have just have some value of g of z with us, which we wrote in our last steps. So this is the value of g of z which we have. So similarly in this step, if you see, we have g dash z which is coming up. So if you try to recall, g dash z is basically derivative of this function, right? So if you recall, so this function is, since u into v form, in u into v form, we can simply say its derivative will be this function into derivative of this function plus this function into derivative of this function. So that's the u into v rule which we basically use in our 11th 12th standard. So let's try to use them over here and let's try to wind up with our answer. So again, recalling what our final intention over here is, just to get the answer 0. So since we need to prove n1 and n2 both are same in number, we just need to prove that this difference should land up to 0. So just try to get that 0 now. So yeah, 1 upon 2 pi I integration over c g dash z. So as I said before, my g of z, let me write it somewhere over here. What is my g of z? So my g of z is h of z into f of z, or f of z into h of z, we can say anything. So this is something there with us. So let's try to use it over here. So it's simply a derivative of this. So let's use the u into v rule. So it's basically says first term and derivative of second function plus second function, or we can say derivative of first function times second function. So that's how we use the u into v rule in school days as well. Coming to the denominator, we have this g of z with us. We have value of g of z as well. Let's put it over here. That is this thing plus f of z. So we just substituted all the values over here, dz, and still the second part of this entire line, we don't have any values for the second part. Let us keep it as is. Let's keep it as is. Let me write this as f dash z upon f of z dz, right? So let's try to proceed further how to get the final answer. So yeah, let me proceed further. So I can just write this, right? So yeah, we can split this denominator, or else you can also simply see that there is something which can be taken common out. Hey, am I missing something? Right, I am missing something, right? So since I took this derivative over here, I missed this part, right? I missed this part. So let me write it somewhere over here. Plus f dash z. So we don't need to miss that part as well, right? This is just the part u into v rule which we have applied. And along with that we have missed this part, f dash z. So I have just written it over here, f dash z. Now let's see, is there anything which I can take common out anywhere? Is there anything that can be taken common out. Yeah, if you see over here, this thing and this f dash z both have f dash z in common, right? So we can take that f dash z common out. Anything else? No, that's it. So let's take that common out. Let's take them common out. So I will have something like this with me, 2 pi I integration over c. If I take that f dash z common out, what will be remaining with me? H of z plus, I am taking this out, right? So I will have just 1. And what else there with me? I have this part, that is plus h dash z into f of z. So in the denominator as well, we have something which we can take common out. So this is something which both the terms in the denominator have. Let me take it common out as well. So if I take f of z out, what will be remaining with me is h of z plus 1. So you guys might have noticed something, this is something in common. So if I split the denominator, I can cancel them off. Yes, it is exactly right, that we will be doing in our next step. And let me try to write the second part as is, minus 1 upon 2 pi I integration f dash z upon f of z dz. Fine. So we are almost done. We can just split this denominator so that we can cancel this off, and let's see what will happen with the second part. So along with splitting the denominator, I will do one more thing. I will split the integration as well. So let's try to do that. So when I split this denominator over here, this entire bracket will get cancelled off, and we will have just f dash z upon f of z, right? And let me write this dz over here. And the second part, I will have this constant which is there outside again with me, integration c. Second part is basically the part with this thing, right? So this thing and this denominator. So let's try to do it. So when I give this denominator to this part, this f of z will get cancelled off, and we will have just h dash z upon h of z plus 1 dz. So that's the thing which will be remaining in the second part when we split the denominator. And let's try to write the last part as is, 1 upon 2 pi I, 1 upon 2 pi I f dash z upon f of z dz. So if you notice something, there is something in common which we can cancel off. Yeah, it's exactly right. This is the two part which is there, which we can cancel off. This thing and this last part, we can just cancel them off. So what's remaining with me is simply 1 upon 2 pi I, 1 upon 2 pi I integration over c h dash z upon h of z plus 1 dz. Fine. So we are over here now. Still we don't have the denominator 0, right? My bad, not the denominator. We don't have the entire value as 0. So let's try to figure out how we can land up saying that this value should be 0. So over here there is something which we need to recall, that is the Cauchy's theorem. So let's try to recall that. What does Cauchy's theorem state? So as per Cauchy's theorem, if you might remember, as per Cauchy's theorem, if f of x or f of z, we can say if f of z is analytic over closed curve C, over closed curve C, then integration of of that function over that closed curve C dz will give me answer 0. So this is the main part which this is the main theorem which we will use in order to conclude our proof. So as you can see, I have I just said before, right, the use of this h of z which I written down over here. The use of this h of z is coming, we will be using that h of z over here right now. So as you can see, h of z is an analytic function. So since it is an analytic function, its derivative should be analytic, right? So what does this mean? The numerator of this part should be analytic. Since h of z is analytic, h of z plus 1 should be analytic. So taking that into consideration, my numerator and denominator both are analytic. So if I divide them, obviously the division should also be analytic. So since this entire thing is analytic and over a closed curve C, using this particular theorem which we stated right now, we can say that this integral part is nothing else but 0. So that's how we will be winding up our proof. Let's write it down straight away. So we can say that since h dash z is analytic and since h dash z is analytic, so is h of z plus 1 h of z plus 1 is also analytic. So we can say therefore integration over c h dash z and h of z plus 1 dz will have the value 0. So if I put this 0 over here, what we will get? 1 upon 2 pi I into 0, and that's our answer. So we can say therefore, so from where did we get this entire thing? So we were starting from right from beginning, n2 minus n1. So we can say our n2 minus n1, is nothing else but 1 upon 2 pi I, right? So 1 upon 2 pi I, this thing, into this integral part which I have right now stated. This is nothing else but 0 because of Cauchy's theorem. We can say, right, we can say by Cauchy's theorem. So just to justify by Cauchy's theorem, we can state this particular thing. So we can simply say this into 0 will give me answer 0. So we are saying nothing else but therefore n2 is equals to n1. So if we want to wind up, we can simply say that what is n2? n2 is the number of zeros with the function g of z plus f of z. And what is n1? n1 is the number of functions, number of zeros for the function f of z. So what we are basically stating over here is the number of zeros with both the functions are equal. So that conclude our proof for Rouche's theorem. So guys, I think you have got the entire proof. So I have tried to explain this entire proof in the simplest possible way. So what I will do is I will put a link in the description where you can just click and get entire PDF which I have written right now. It will be more handy for you to refer. Thank you.